this again. So one of my goals in this class is you'll learn enough chemistry, and specifically today that you'll learn enough chemistry, that you can start to correct really bad memes. Like, this is totally wrong. That is not sodium bromate, okay? That's sodium hypobromite, okay? So this, anyway, so next time you see that meme, you're like, no, that's not correct. So that's what we're going to be focusing on today is naming with those oxoanions, and then we're going to get into the acid naming because that's also on Monday. So we're going to start naming acids today. There's a slightly different set of rules for naming acids as there were for the covalent compounds and for the regular metal, non-metal salts, and then for the oxoanions. So let's jump in. So Alex reports, again, I realized that we just finished a homework on Wednesday. So when I checked yesterday, the day after the homework was due, not a lot of people had started with it. So I was like, not good. But then I was like, oh, well, it is due Monday. But still, get on it early because, you know, you may have plans, right? Something may happen this weekend that you want to do. And if you get started on Monday's homework today, then you kind of bank a little leisure time and you can be ready for it. Says you're ready to learn. Almost everybody's ready to learn naming hydrates and things like that. So we're going to be talking about hydrates today too. So we're good shape. So good job on that. So what are the topics that are due Monday? These are the ones that we covered in the video lecture on Wednesday. Here we are today on Friday. Before we go on, though, are there any questions that are popping up that on the ones that were due Wednesday? Or the naming stuff it seems pretty straightforward. Would you agree with that? You just got to identify the anions mostly. They're the ones that create trouble. And the cations, whether you'd use a Roman numeral or not, that's always a question.
Can we get clarification on that?
Yeah, so in the set of lectures, I don't remember if it was the last one or previous two ago, I have a periodic table that shows like green boxes on all the ones that don't have Roman numerals, and the red ones had Roman numerals. So it just really is simply whether or not it forms ones like, this is the way your book has it, and you can see here there's mercury 2, chromium 3, and so on. So the ones with Roman numerals are the ones you have to have Roman numerals on, and the ones without Roman numerals you don't have to have Roman numerals on. So this table has it all that you need. Yeah. And that's why I was promoting the Quizlet flashcards. Those are more for the anions, but I think I might have cations on there. I'm not sure. But you can also search for Quizlet card sets, and I guarantee people have made card sets for cations and the anions. Not necessarily in my class, but in other classes. The only one that really gets a lot of students, in my opinion, is this mercury 2 here, Hg2 plus, or the Hg2 2 plus. So when it has the subscript 2, that's mercury 1, because 2 atoms are sharing the 2 plus charge. So that one is really weird, you know, if you're not paying attention. So you see the Hg subscript 2 plus, that's mercury 1 cation.
So is the mercury, is that the same thing as with oxygen? How you like have to have this like 2 oxygen?
Oh yeah, so for these, it'd be interesting. So you could write, yeah, so in this case, you'd have 2 different compounds. Let me try to find Hg2O and HgO. So if I'm looking at these 2 compounds and I have to name them, okay, I'm going to go with the oxygen first because I know the charge on oxygen, right? I'm looking up there, I see oxygen is in group 6. That's 2 away from group 8. So it wants 2 electrons. So oxygen's always going to be 2 minus. So I know that both kinds of that mercury business is charged 2 plus, right? And so in this case, I've got oxygen 2 minus and Hg2 plus. And I've only got 1 mercury atom there, and it's 2 plus, so that's mercury, M-U-R. Let me use my eraser 1 or 2? What do I put?
Two.
2, because that's the charge on the mercury ion oxide. Okay, up here, this is, again, oxygen's 2 minus. So this whole thing is 2 plus. That means each individual mercury atom is just a 1 plus. And so that's going to be the mercury 1.
And that's just for mercury.
Yeah, none of the others do that. That's why I emphasize it so much, because it's a weird one. It's kind of the exception. Right? So mercury 2 plus, or the mercury 1 cation is a polyatomic cation. It has 2 atoms in it. The only other polyatomic cation is ammonium ion and hydronium ion. So we have 3 really. So ammonium ion is here, NH4 plus, again, multiple atoms, so we call it polyatomic cation. And then also H3O plus, H3O plus, and that's hydronium. I just want to keep putting that one in there because we're going to run into that when we get into acids and bases. When a proton comes off of an anion to make an acidic solution, it gets snatched up by water. And so if I add a H plus to water, I get H3O plus. Okay, so that's what's going on with acid-base chemistry. Okay. Y'all think about your questions? Let me close the door. Okay, what questions? What other questions? These are good. And we've got time for them today, so don't worry.
What's the tutoring place's name? Because I had this work in technology. I learned it there, and then I completely just forget.
Okay, so how to deal with that? You've got to find something interesting about it, and I know that's tough. It's just naming acids and stuff. So let's have fun with this. When is our exam? It's next Friday. So we got a lot of time for review. I may have messed up the schedule a little bit because we're going to just really beat this stuff pretty hard and be done with it. So Monday I'm going to cover a little bit more with naming acids, and then Wednesday will be total review. Okay. So let's do this for Monday. If you'll bring a picture of something that has a chemical name on it that you now know from our class, okay, then you get a sticker. What can I do, right? But we'll have everybody bring a picture on your phone of something, a shampoo bottle, whatever, that has a name on it that we've learned in class. Okay? And then I'll run down, I'll look at your phones, you can pick your stickers, and it'll be really fun. Okay? You can stick it on your little notebook or whatever. If you do everything electronically, I don't know, maybe you can put it on the back, don't stick it on the front. And so we'll have little small stickers. Okay? I like to have them just for that kind of thing. Somebody asks a really insightful question or catches me in a mistake, like if I got a really glaring mistake, and you say, "Excuse me, I think that should be a 2 instead of a 3 or something," then you get a sticker. Okay, so to keep those with me. All right, so that's it's kind of fun. So we'll do that for Monday. So bring a photo of something that has to do with the naming that we've been working with. Here's your anions. Like I said, you just got to know these because this is the vocabulary. It would be like taking a foreign language and not knowing your verbs. Okay, you got to know your verbs. So let's use these. So this is, again, we've done a lot of these kinds of problems where you get the formula and the name, but now we're adding in those polyatomic anions, those oxoanions as well. So there's a lot of, just got to drill. So what are we looking at here? We're looking at iron here, iron 2 plus, and so we're going to need some parentheses on this NO2. So we've got iron nitrite. So this is the NO2 minus. The base model oxoanion for nitrogen is NO3 minus, and so that would be nitrate. And this has 1 less oxygen. So we find the nitrate. We've got that memorized, NO3 minus 1. If I just take away an oxygen, it's NO2 minus 1, and I've gone from 8 to ite. I've gone down 1 step, 1 oxygen, and so the 8 becomes an ite. So this is iron 2 nitrite. Calcium and sulfate are nice because it's a 2 plus and a 2 minus, so I don't need any parentheses for this one. So I'm just going to make calcium sulfate, CaSO4. No parentheses needed. Okay, and calcium, how do I know if I need the Roman numerals or not? Do I need them for this one, for the calcium? No. Why is that? Yeah, it's in group 2, right here. So these are all 2 plus. Why? Well, because they're in group 2. If I subtract 2 electrons, they become group 8. They have the electron cloud, they're isoelectronic. So calcium, if I take away 2 electrons from calcium, then it has the same electron cloud as argon. You see, argon is 18. Neutral calcium has 20 electrons. If I take away 2 of those, I have 18 electrons, same number of electrons as argon. Argon has a really stable electron cloud. So calcium ion is as stable, if you want to think of it that way, as argon electron cloud. But it has 2 more protons, and so it's positive 2 charge. So this is calcium sulfate. That's sort of the base level of your sulfur oxoanion. So SO4 2 minus. If we were to have SO3 2 minus, it would be sulfite. Barium 2 plus, group 2. Not going to need any Roman numerals. Okay, and it's ClO minus. So again, I can't. If I'm having trouble memorizing these, I can at least memorize chlorate, bromate, fluorate. All of those in group 7. The base model has 3 oxygens. So chlorate has 3 oxygens, bromate has 3 oxygens, fluorate has iodate. All those 8s have 3 oxygens, and they're -1. And so if I take away, then it's chlorite. And if I take away another one, it's hypochlorite. It's even less than chlorite. So this would be barium hypochlorite. But you saw how I got there, right? I started with the base model of the chlorate. Took away 1, that's chlorite. Took away 2, that's hypochlorite. Okay, then the next one's manganese. And then we're going to need 3 of those negative charges. I'm not telling you the name of this one yet, because again, it's in group 7. So all of those group 7s, how many oxygens does the base 8 oxoanion have? I just talked about it. 3, right? So chlorate was ClO3. If I have BrO3, that's bromate, and this one has 1 more than that. So then I add that prefix per. So it's per bromate because it's got more oxygen. So that's manganese 3 per bromate. Okay, so we did it. I realize this isn't so exciting. It's just going over the names. But what I'm trying to do is teach you my logic and how I remember them. Because I do still have to go through this sometimes. I hit a weird one, like I don't see bromate per bromate a lot in my studies as a scientist, right? But so I come across it and I'm like, okay, how do I get to this? I know the BrO3 would be bromate, and so this has 1 more, so it's got to be per bromate. Okay, example 2. So here's one where we do the crisscross. So how do I come up with the formula on this one? I've got a 3 plus cation and a 2 minus anion. So I'm going to have to get this common factor of common multiple of 6. So I have a 3 here. I'm going to put that in parentheses. Okay, and then I've got a 2 here. Okay. So anytime you have that 3-2 combination, you're going to crisscross those, and those will be your subscripts. So this is the empirical formula, Fe2SO4 with the 3 subscript. Okay. And if you didn't remember that, don't worry. Just now you know it, okay? So anytime you see that 3-2 combination in the charges, you're going to swap them down, crisscross them, and that's how many ions you need, because you have to have the same number of positives as negatives. So I've got 2 3 plus cations, that's a +6, and I've got 3 minus 2 anions, that's a -6. So they balance out. Okay, for naming, SO4 2 minus is sulfate. This is iron. Iron has to have a Roman numeral because there's iron 2 and there's iron 3. Those are the typical ones. So this would be iron 3 sulfate. Okay. The next one has ClO3. That's chlorate. And the cobalt is a +2, so I need 2 of those chlorate ions. Oh, I've got a little typo there. It should be CO, not Ca. So this should be an O. Cobalt 2 plus, cobalt 2 chlorate. So now this one is not NaBro from that thing, it's NaBro 2. So it's sodium. And now what are we going to do with this ion? It's not BrO3, that would be bromate. It's got one less, and so it would be bromite. So H drop to ites when they lose an oxygen. So this would be the NaBrO2. The charges match, so we're okay. We don't need parentheses. So that's sodium bromite. Okay. And then now we have that NO3 minus, that's going to be the nitrate. So don't need any changes in the prefixes or suffixes. But I need 2 of them because the magnesium is a 2 plus. Now magnesium is in group 2 there by sodium, so I don't need any Roman numerals. So magnesium nitrate. Any questions on these? Yes.
So whenever you're naming the compound, do you only use per if it's like in group 7 or if it just has 4?
I think it's only the group 7 that we see that, because nitrogen is really small, and so we can't get a 4th oxygen on there. So nitrate, if we could get to NO4, it'd be per nitrate, but it's so small, you can't get we can put 4 oxygens on chlorine, bromine, and iodine because they're huge. Did I do the target ball, the size of a hydrogen atom in here in one of my lectures? I didn't. Shame on me. So look, I can tell you the story. Okay, one day I was walking into Target with my family, and my kids are used to this. So I saw the big red ball in front of Target. You know what I'm talking about? To keep car bombers from driving in the front door. That's really what it's for, a little security. So this big red ball in front of Target. I thought, what if that were a proton? How big would the hydrogen atom be? So where's the 1s electron on the hydrogen? How far out does the hydrogen electron cloud go on a 95% basis? You know, there might be a 5% chance the electron's further away. But a lot of times we'll draw a line around the atom or molecule at the 95% line. So 95% of the time, the electron is inside this surface. Makes sense, okay. The 95% size of a hydrogen atom would go from Madisonville to Spring, and from I guess Livingston over to Navasota, 71 miles across. So when we say that we're mostly space, that's true. Our nuclei, where all our mass is, an electron, a proton is 1,000 times heavier than the electron. So 99.9% of the mass is that target ball. And the 1 part per thousand mass is spread out from Madisonville to Spring. Anyway, that's the size of a hydrogen atom. Chlorine, bromine, iodine. I think I did it for sodium. That 3rd electron in sodium is about as far out as the size of Texas. So sodium is as big as Texas. And you see bromine and iodine are even bigger than sodium. So they're getting, again, if the nucleus was that ball at target, the bromine nucleus isn't that much larger, but the electron cloud is probably the size of the planet. And so I could put a lot of oxygens around bromine, but I can't really put them around nitrogen because nitrogen's still pretty small. And oxygen's, comparable size. But size does start to play a role in those smaller, on the 2nd row. But once you get to the 3rd row and higher, chemistry gets more interesting and more reactive, and you can do more things. Okay. So that's also why the stability of those, like all of our carbon compounds or nitrogen and oxygen compounds are super stable because they're really small and they're really tightly bonded. Yeah. So that's why we don't have a per nitrate, to get kind of back to your question. Yeah. But we do have the per bromate, per iodate, and per chlorate. I don't know if we have a per fluorate because again, fluorine is really small. And so we might have fluorite and hypofluorite, and we might have fluorate. Okay. Cool question. Okay, let's do another one. Okay, so here we have the barium hypobromite. Okay, so barium's 2 plus, BRO 2, barium, and again, this is 2 oxygens down from bromate, and so it's going to be, what happened? Why did it come in last here? Okay, hypobromite. Okay, so let's go back up here to lead. Now here we have the 3,2 thing. Okay, we got a lead 2 plus and a PO4 3 minus. So we're going to swap those subscripts. I'm going to end up with a lead with a 3 down here and a PO4 with a 2 there, and I'm going to use the parentheses. And that's lead 2 phosphate. So PO4 3 minus is the 8th form of phosphorus, phosphate. Again, what would be the phosphite one? If this is phosphate, what would phosphite be? PO3. And then what's the charge? The charge doesn't change. So it would still be PO3 3 minus. Okay. And then here's sodium nitrate. So NaNO3, sodium nitrate. That one's straightforward. Okay, this one is a lead 4. So we need 4 of those okay, what is this one? It's not iodate. I nearly messed up. It's IO4. So again, the iodate would be 3. I've got 1 more, so that's per iodate. It looks like period, but it's per iodate. Periodate. Per iodate. Any of these throw you? Okay. Good. Okay. There's the hypobromite. Okay, so now the book, and Alex started throwing in it had suggestions. So I was picking the ones like the naming oxoanions and stuff. I was like, yeah, I want to have that. Yeah, I want to have that. And Alex suggested hydrates. Okay, it's kind of, I'm not sure if the other professors teach the naming of hydrates, but here's why it's important. So I went ahead and included it because it's easy, but also because it is really important if you go to the lab. So it's important to connect the name of the formula with connect the name of the compound to the formula, because what you need to know when you weigh things out. So if we have copper 2 sulfate, right, then we know that's CuSO4. So you can write that down, CuSO4, copper sulfate, copper 2 sulfate. And we know that gives 1 mole of copper ions in each formula mass. So if I weigh out that formula mass, I've got, and so what's the unit of things that we weigh out in chemistry? We haven't really covered the mole concept in class yet, but think of a mole like a dozen. We're not going to do reactions with a single copper ion. We're going to do it with a measurable mass. And the measurable mass of atoms is called a mole. Just like a simple way to buy eggs. You don't buy an egg 1 at a time. You buy a dozen at a time. So we don't weigh out single atoms. We buy a mole of them and weigh them out and use them in moles. So that's sort of the unit that we use for moles. The periodic table, all of those masses are the mass of a mole of those ions or atoms. Okay. So to come up with the formula mass, I have 1 copper. I look at the table. That's 63 and a half, okay, grams per mole. And then I have 1 sulfur. So I look at the table. It's at 32.1 grams per mole. And then I add up 4 of the oxygens. So I have 4 of those. They're 16 grams apiece. So I'm going to multiply that by 4. Add that up and I get my mass. 159.6 grams per mole of that formula. So I get a mole of all of those atoms and 4 moles of oxygen if I weigh out 159.6 grams. Now, how would I get that? Well, I would go to the stock room and I would get a bottle of copper sulfate. And I go to the balance and I'd scoop it out and weigh out. If I wanted a mole of copper ions, I'd scoop out 159.6 grams. I wouldn't scoop out 63 grams because it's not pure copper. It's copper sulfate. So I need to know what the stuff is. If I want a mole of copper ions, I got to know what to scoop out. And the formula mass tells me what to scoop out of the bottle to get a mole of copper ions. Say I'm doing some experiment with copper. Okay, this is why the hydrates are important. Because if I go to the stock room, this is what I see. Beautiful blue crystals. Okay, but I look carefully at the bottle, and what do I see on the bottle? Copper 2 sulfate with a really important word after it, pentahydrate. Okay, so those crystals are not pure copper sulfate. They have water in the crystal structure to make this beautiful blue crystal. So it changes things. I've got to scoop out something different now because it's not just CuSO4. So that's why I think that Alex wants us to push this into your class, because it's really important as a chemist to know when you have a hydrated crystal like this, you got to calculate the formula mass that includes the waters. Otherwise, you won't get all the copper that you think you're getting. Okay, so let's look at the math. This is actually copper sulfate .5 H2O. So that's the real structure here. The formula mass for those crystals have those 5 waters in them. Where'd I get the 5? Penta, exactly. So you already know those from the non-metallic molecules like dinitrogen tetroxide or tetroxide. So you already know the monodi thing. And so you just do that with the waters. So the naming is super easy. This is copper sulfate pentahydrate. So you just add the pentahydrate on there. Okay. And then you can communicate with people. Say, go to the stock room, get you some copper 2 sulfate pentahydrate, and then calculate what you need to weigh out, and then give me a mole of copper ions. And so then you can do that because I've told you exactly what you're looking at. So let's do the math on that one. So this is copper 2 sulfate pentahydrate. And that's there's the structure, copper 2 sulfate pentahydrate. So we're just going to take what we already did, that copper sulfate 159.6 grams per mole that we calculated a few minutes ago. And we're just going to add in 5 grams per mole of 5 of the water. So how much does water weigh? I did this one in my head to get to the 18. So look at oxygen. We go over to here. Oxygen is 16. I realize you can't see that little tiny number in the back, but that oxygen below says 15.999 something or other. So I'm going to say 16. And then I go over to hydrogen, and it's 1 each. So I got water. Okay, 16 for the oxygen and another couple for the hydrogen. So 18. So that's where I got the 18. 18 is not on the periodic table, but the H2O is 18. So 16 for the oxygen, 2 for the hydrogen. And I got 5 of those. So I'm going to take the 18 times 5 and add it to the 159.6. So this is the formula mass for copper sulfate pentahydrate. This is why it's important to know how to name the hydrates, because you're going to come across them in the stockroom. Okay. So this is the mass I need if I want 1 mole of copper, because this whole thing has 1 mole of copper in it. So I weigh this whole thing out. If I didn't do this, let's look at the problem. If I wanted a mole of copper and I only weighed out 159.6 of the pentahydrate, I weighed out 159. I should have weighed out 249. So right at the beginning of the experiment, I've only got 60.64 moles of copper. I got 64% of what I was looking for. In other words, I'm off by the 1 minus that. So what would that be? 36. Yeah, so I'm off 36% before my experiment even started. So if I was trying to calculate my yield and all these different things like that, and I'm like, man, I just can't get any better than 64% yield. What's wrong? It was because at the very beginning I started with the wrong mass and everything was off. Okay. So this is why we need to know about hydrates. Okay, so here's the bunch of examples from Alex, and it just shows an example of all of those, like sodium carbonate, monohydrate, and we just use those dots. Now, notice it's kind of strange to use a dot, but what we're doing with the dot is we're just saying that this isn't part of the chemical. I want to say it's not part of the anions and cations, right? It's just sort of tacked on, and it's part of the crystal structure. But if you were to heat these up, you could dry them out. You could get rid of the hydrates. You could dehydrate them. So if we heat them up hot enough, then those waters would come off, and we'd have just copper sulfate or sodium carbonate or whatever. Okay. But a lot of times these are precipitated out of water. We let the water evaporate, and these crystals start to form, and they have the hydrates in them because they came out of water. Then we have the next one's calcium sulfate, .82H2O, so that's calcium sulfate dihydrate. Surely you should be able to go from this right column to the left one. So here we have aluminum nitrate nonahydrate. So I see that noni, which is 9, and so then I should be able to write aluminum nitrate. I need 3 of the nitrates because they're -1 each, .9H2O. So that would be the structure. Any questions on this? Yes.
Isn't water dihydrogen oxide, right?
Yeah, that's.
And so-
But it's so common that we just call it water.
Well,
Yeah.
So you don't have to accumulate for the subscript 2 when you name it at all? 'Cause
No.
right, that would be- okay.
Yeah, we're just saying hydrate for water. Yeah. So this is yeah. In this particular case, we just call it hydrate. So it's dihydrate or trihydrate. Yeah. But yeah, that's so yeah. Sometimes it's called water. Sometimes it's called hydrate. But I don't think ever in chemical naming it's dihydrogen monoxide. I mean, that's sort of just rigidly applying the rules to water, but it's never really called that, except in a couple of like internet jokes, you know, like trying to get congressmen to ban water because they talk about how many people have drowned from this substance. People breathe this substance in and it kills them fairly rapidly. They go through and they try to get them to ban dihydrogen oxide and dihydrogen monoxide. Yeah. So that goes around the internet. You might catch it on an email or something from a friend. Yeah. Okay, let's change gears a little bit and talk about acids. Acids are proton donors. Now that sounds really strange, but a hydrogen atom that loses its electron is a proton. Okay, because hydrogen only has a proton and an electron. If we put hydrogen onto chlorine, and it wants to react with water, water can easily steal the proton, and chlorine wants that electron because chlorine has a stable, if a chlorine anion, it's the same electron cloud as argon, okay? So it's not gonna let hydrogen take that electron with it. But water can steal the proton and chlorine doesn't care because chlorine has such a stable electron cloud. Same with all the anions, like phosphate and all kinds of things. They'll let the protons go, but they're anions, and so they want to keep those electrons because those are really stable substances. So you can make an acid from all of these anions. Just put a proton on there, an H+. When you put an H+ on here, it cancels the minus, and you get a neutral compound. So how many H+ do you put on? However many minuses you have. Like here, phosphate. So if I want to make phosphoric acid, I put 3 protons on here, cancels the 3 negatives, and I have a neutral compound. So H3PO4 is phosphoric acid. If I had H2SO4, so this sulfate is a 2 minus, H2SO4, sulfuric acid. So all these anions can be made into acids by adding the number of protons to cancel out the charge. Even over here, now there's some weird ones, like if I put 2 protons onto this oxide ion, I end up with water. So I don't end up with hydroxyic acid. Yeah, trying to make the name in my head. Yeah, and then also the hydroxide ion. If I put a proton on there, I end up with water. So a couple of these just end up being water. Okay, but for the others, like for chloride ion, if I put a proton on there to cancel it out, I end up with HCl, and that would be hydrochloric acid. If I put a proton on the bromide, it would be hydrobromic acid. So there's some trends here that we'll talk about. So there's really 2 types. There's the single ions like the fluorine, bromine, we call those binary acids, and they are named a certain way. And then all the others with oxygen in them, we name them a slightly different way. Okay. So let's learn those rules. So the naming rules depend upon the anion. There's 3 types of rules, really 2. Binary acids combine a proton with a single element anion like HF or H2S. Okay. And then there's the oxo acids that contain oxoanions plus 1 or more protons like nitric acid or NO3, HNO3, or nitrous acid, HNO2. So OUS, we haven't come across that one before. Okay, so we'll learn that today. And then they have other ides and ates, right? Oxides and bromides and everything, and nitrates and bromates. So let's go through the binary acid naming rules. So this is what it is up here at the top. Hydro plus the anionic group and then ic acid. So something acid. So fluorine or fluoride, if we make an acid out of the fluoride ion, we have hydrofluoric acid. So notice how we have the hydro in front for all of these. So chloride, we put a proton on that, it's hydrochloric acid. For sulfide, even though there's 2 protons, we add 2 protons on there, but it's still binary in that it's a hydrogen and an element, like the sulfur. And so this one is just a tiny bit of an exception. Instead of hydrosulfic acid, which would be a rigid following of the rules, it's hydrosulfuric acid. So they add that extra UR. Okay, so that's what the little note is down here at the bottom. So H2S is hydrosulfuric acid. So we don't say H2O though as hydroxyic acid or hydroxydic acid because it's water. Okay. Any questions on these? We'll apply these to some examples here at the end. Okay, so these are the binary acid naming rules. Pretty straightforward. If the anion is a single element, no oxygen. Okay. What if it has oxygen? So then we have the nitrates, nitrites, perbromates, and so on. So if we make acids out of these, we need to look at this right here. If it's let me just put a big box right here. This 8 and ite. So if the anion ends in 8, then it becomes something ic acid. Okay. So nitrate becomes nitric acid. Bromate would become bromic acid. Chlorate would be chloric acid. So, and even the perbromate would be perbromic acid. So anything that ends in the ATE, you take the AT off and put an ic acid on there. What about ites? So if we have nitrite, ITE, then it's nitrous acid, OUS. So ates become ics and ites become us's. So there's no rationality behind it. It's just the trend. It's just the way we as scientists have named these things. Okay, and then here we have hypoiodite, and that's hypoiodous acid. Sounds strange, but that's the correct way to name it. Once again, the sulfur is the weird one. So you go from sulfate to sulfuric acid and sulfite, SO3, to sulfurous acid. So we have that extra UR in the sulfur. So just these are your examples. I haven't done any of the Alex examples of the naming because, you can take these examples and apply them to Alex.
Is there any other element or anion that does it like sulfur? Or sulfate?
I'll pull up the anion list and we'll look. It's a good question. Let's do the last deal and we'll do that, so I'll remember that. Okay, then there's other ides and ates that don't have oxygen, okay? So like Cn minus. In your list of anions that you've memorized, You know, that's the cyanide ion, okay? Okay. And so since that ends in an IDE, just like chloride ends in an IDE or fluoride ends in an IDE, it's going to be a hydro something ic acid. So it's going to follow those same rules. Since it's an IDE, we're going to pretend that it's like a bromide, chloride, fluoride, and so on. So this is cyanide, so we're going to call it hydrocyanic acid. So that's why this is, it's kind of using the binary naming rules if it ends in IDE. Okay. And if it ends in ATE, like thiocyanate, okay, SCN minus, then we're going to take that 8 off and put an ic in. So it's thiocyanic acid, HSCN. And then acetate, there's so many different ways to write the acetic acid ion, but they put the hydrogen in front here. This is the acetate anion with the proton on the front. And so the ATE becomes ic, so acetic acid. And then here's oxalate anion, and it becomes oxalic acid. Since the ATE, it becomes oxalic acid. That's straightforward, but we'll look at the anion table here. So the good question, let me find that. So the question was, are there any other, which ones?
Any other elements that are
Like sulfur. Yeah. So let me look at that. Oh, here we go. Here we go. Hydrocyanic acid. Chromic acid, dichromic acid. Yeah, okay, phosphoric acid. Okay, so here, okay, there's a little lag here. I was trying to find my pen. Okay, so this one is right? So it has this extra OR. So kind of like sulfuric has the extra UR, phosphorus, the phosphate, we don't just take off the ATE and put an IC, we add that extra OR. So it's phosphoric acid. This is H3PO4. Okay. Phosphoric acid. So that's carbonate would be carbonic acid. That's following the rules exactly like they're stated. Perchlorate would be perchloric acid. Chlorate would be chloric acid. Yeah, so all of the others, sulfur and phosphorus. Those are the two ones that have an extra syllable and then in the acid name. Okay. Because otherwise, you know, like if you were applying the rules exactly where we take the 8 off and put IC, that it would be phosphic acid, and that's not right. Okay. And the same with sulfur, it would be sulfic acid, and that's not right. It's sulfuric acid. Okay. Yes.
So for how come for hydrogen peroxide we don't call it hydro?
That's a good question, yeah. So I guess it boils down to it not being a very good or very strong acid. So it's very reactive, but it really kind of breaks between the oxygens, or it'll donate a whole hydrogen, not a proton. So it's kind of a bizarre molecule in that respect. So we just don't name it with the acid rules because it behaves more as a molecule reacting in different ways than acid-base ways. Yeah, but I have never had that question before. That's great. So H2O2 is it'd be hydrogen peroxide. Yeah, not what would we call it? Hydroperoxic acid. Yeah, trying to follow the rules on that. It's so hard for me because I've never heard that before, hydroperoxic acid. But yeah, I've never heard that before. But like like if I had to squeeze that round peg into a square hole, that's what it would sound like. Yeah. Okay, good. Time for a few more questions, yes.
So, whenever you're like when you're having to name a compound or element,
Yes.
how do you know if it's I or I, like all the
Yeah, so that's where you have to find a foothold. And so I would memorize all the eights. So there's a figure, there's like 6 of them, 5 or 6 of them, where it starts with chlorate, okay, ClO3 minus. Then go left, it's sulfate, SO4 2 minus, okay. And then to the left, it's PO4 3 minus. Notice the charges increase, 1, 2, 3 as you go left. And then when you go up to nitrate, it's NO3, just a single minus. And then carbonate is CO3 2 minus. Yeah. So those are 5 that you can memorize. And then if you go down 1 oxygen, you have the ite. You go down 2 oxygens, you have the hypo something ite, right?
Alex has a good explanation.
Yeah.
When you get to those problems.
Yeah, and so there's a figure too that I like snapped out of Alex that shows all 5 of those that I just walked through, and it has like a little scheme. So it's in the notes. Yeah, probably 2 lectures ago. When I'm talking about those oxoanions, then you'll see that scheme that I'm talking about. So that's how I do it. I memorize the 5 eighths, and then if I'm going up, like on the chlorate, it's per chlorate. So I've got ClO4. I've memorized the 3rd one. Okay, so when I have 4 oxygens, I know it's perchlorate. When I have 2 oxygens, I know it's chlorite. And when I only have 1 oxygen left, it's hypochlorite. So that's how I remember it. So if you know the eights, then you can go up and down. Yeah. All right, great. Y'all have a good time.